In Lecture 6 we introduced the inverse trigonometric functions, and as we all know, sine of x, cosine of x, and tangent of x are not one-to-one functions. So in order to create inverses for them, we must restrict their domains. So for example, for sine of x, the restricted sine function is the function f of x. It's a piecewise defined function, and it's defined as sine of x between minus pi over 2 and pi over 2, and it's undefined otherwise. Pardon me. We have the domain of this piecewise defined function, the restricted sine function, is everything between minus pi over 2 and pi over 2, and its range is everything from minus 1 to 1. We see here on the left the graph of y equals sine of x between minus pi and pi. It's most certainly not one-to-one. It doesn't pass the horizontal line test. And on the right we have the graph of the restricted sine function, which is just the restriction of that sine wave to the interval between minus pi over 2 and pi over 2, and that is a one-to-one function. Therefore, it has an inverse function, and we call that inverse function sine inverse of x, or arcsine of x, not to be confused with 1 over sine of x. Here in blue we have graph of the restricted sine function, and we also have in red its reflection in the line y equals x, which is the graph of our new function y equals arcsine of x. Because the point pi over 2, 1 is on the graph of the restricted sine function, we have the point 1 pi over 2 is on the graph of sine inverse of x, and that means that sine inverse of 1 equals pi over 2. Algebraically, we have the domain of sine inverse of x is all numbers between minus 1 and 1, and its range is all angles between minus pi over 2 and pi over 2. We have the algebraic description of it. Sine inverse of x is y if and only if sine of y equals x and y is between minus pi over 2 and pi over 2. So y is that unique angle between minus pi over 2 and pi over 2 whose sine value is x. Because of how inverse functions work, we have sine of sine inverse of x is x for any x between minus 1 and 1, and sine inverse of sine of x is x only if x is between minus pi over 2 and pi over 2. We see from the graph that sine inverse of x is an odd function. Sine inverse of minus x is minus sine inverse of x. In class we'll evaluate some examples. And we'll also look at this problem, which prepares us for the method of trigonometric substitution in methods of integration. And basically, to give a formula for tangent of sine inverse of x, we create a right-angled triangle with sine inverse of x as an angle in that right-angled triangle. So we have sine inverse of x equals theta. So therefore, sine of theta must be x, which is x over 1. So we make the length of the opposite side x, and then the hypotenuse has to be 1 if theta is sine inverse of x. And then by Pythagoras' theorem we have this third side equals the square root of 1 minus x squared. Now we see that tangent of sine inverse of x is just tangent of theta, which is the opposite over the adjacent. And that gives us a formula for tangent of sine inverse of x in terms of x. We can also calculate the derivative of sine inverse of x using implicit differentiation. And in fact, we have the calculation in this set of notes. There we have the properties, and here we have the derivative of sine inverse of x. So we have sine inverse of x equals y is the same as saying that sine of y equals x, and y is between minus pi over 2 and pi over 2. And if we differentiate both sides of this equation, we get cosine of y dy dx is 1, so dy dx is 1 over cosine of y. And now we know that cosine squared plus sine squared is 1, so we have cosine is the square root of 1 minus sine squared of y, or the square root of 1 minus x squared. So we get the derivative of sine inverse of x is 1 over 1 minus the square root of 1 minus x squared for any x between minus 1 and 1. And in class we'll look at how we use that derivative in conjunction with the chain rule to solve more complicated examples like this. We can also create an inverse cosine function by restricting the domain of the cosine function. And at the end of your class notes, you'll see that we have some graphs here. We restrict the domain of cosine to all angles between 0 and pi, and this we create a piecewise defined function called the restricted cosine function. G of x is cosine for x between 0 and pi, undefined otherwise, and here's its graph, which is 1 to 1. And then if we reflect that graph in the line y equals x, we get the graph of cosine inverse, or arc cosine of x. So arc cosine is the inverse function for the restricted cosine, and this is how it behaves. We have cosine inverse of x equals y. It's the same as saying the cosine of y equals x, and y is between 0 and pi. So y is that unique angle between 0 and pi for which cosine of y equals x. We have cosine of cosine inverse of x equals x for any x between minus 1 and 1, and cosine inverse of cosine of x is x for all angles x between 0 and pi. So cosine inverse will always give you an angle between 0 and pi. You can also prove using implicit differentiation that the derivative with respect to x of cosine inverse is minus the derivative of sine inverse. And in fact, you can use that to prove that sine inverse plus cosine inverse is equal to pi over 2. We can also create an inverse tangent function by restricting the domain of the tangent function. So the restricted tangent function is defined as h of x is tangent of x for x between minus pi over 2 and pi over 2. So we restrict the domain of the tangent to everything between minus pi over 2 and pi over 2, and this restricted tangent function is undefined otherwise. And then tan inverse, or arctangent of x, is the inverse function of that restricted tangent function, which is 1 to 1. Here we have the graph of the restricted tangent function on the left, and its reflection in the line y equals x is shown here on the right. That's y equals tan inverse of x, or y equals arctangent of x. We have pi over 4, 1 is on the graph of the restricted tangent, so therefore 1 pi over 4 is on the graph of y equals arctangent. That means that arctangent of 1 is pi over 4. And we have an extra feature here on this graph of the restricted tangent. We have two vertical asymptotes at pi over 2 and minus pi over 2. And when we reflect the graph, we get two horizontal asymptotes, one at y equals pi over 2 and one at y equals minus pi over 2. So this allows us to see what the limit as x tends to infinity of tan inverse of x is. It's equal to pi over 2, because the graph gets closer and closer to the line y equals pi over 2, and the limit as x tends to minus infinity of arctangent of x is minus pi over 2. Here we have the details. We have the domain of tan inverse is now everything, every number between minus infinity and infinity, and its range is the set of angles between minus pi over 2 and pi over 2. Algebraically, tan inverse of x equals y, if and only if tangent of y equals x, and y is between minus pi over 2 and pi over 2. In other words, y is the unique angle in this interval for which tangent of y equals x. We have tangent of tan inverse of x equals x for all x, and we have tan inverse of tangent of x is equal to x for x between minus pi over 2 and pi over 2. From the graph, we see that it's also an odd function. Tan inverse of minus x is minus tan inverse of x. And we also have two limits. The limit as x goes to infinity of tan inverse is pi over 2, and the limit as x goes to minus infinity of tan inverse is minus pi over 2. In class, we'll calculate some examples. And also you can use implicit differentiation to show that the derivative of tan inverse is 1 over x squared plus 1. And reversing the formulas for the derivatives, we also get two new integrals. The integral of 1 over the square root of 1 minus x squared is sine inverse of x plus a constant, and the integral of 1 over 1 plus x squared is tan inverse of x plus a constant. And of course you can use these along with substitution to calculate more complicated integrals like the one shown.